Hello guys, let's see about mossbauer spectroscopy. I have discussed about the introduction in the previous video. This spectroscopy is based upon gamma ray absorption. So it's also known as nuclear gamma resonance spectroscopy. Okay, nuclear gamma resonance spectroscopy. Mossbauer active nucleus possess I greater than 0. So this is the essential condition for a nuclide to be Mossbauer effective. Okay, so let us consider radioactive nuclei. X is a Z is the atomic number, A is the mass number. This one electron capture forms Y with Z minus 1. So one electron is reduced and then Y is Z minus 1 and A is the mass number, Z minus 1 is the atomic number. Okay. One nuclei is converted to another nuclei on the electron capture. So, this nucleus that is produced will be in the excited state. For example, cobalt 57. 57 is the mass number, 27 is the atomic number. On electron capture, it is getting converted to iron 57, whose atomic number is the 26. Okay, so this is in the excited state now. So, excited state will go to the ground state by releasing the or emitting the gamma rays. So this forms the source now. So this process is said to be gamma ray fluorescence. Okay. So gamma ray fluorescence occurs here. So source is cobalt 57 and then the iron 57 in the excited state is a source for the gamma rays here. Then the gamma ray that is produced is absorbed. Okay. It is absorbed by the absorber. Absorber is a sample which is under study. So here absorption of gamma rays takes place. So that is said to be gamma ray resonance. When it will occur? When the energy of the energy levels of source as well as the absorber matches. Then only the resonance occurs. Then signal produced for the transition. Okay. So for the Mossbauer spectroscopy, recoil effect and isomer shift is a basic principle. Recoil energy means whenever high energy particle is emitted from a body at rest, the releasing body will go back, feels a back kick. So that is, it is pushed backwards. That is known as the recoil effect. Energy used for this recoil effect is known as recoil energy, that is equal to E gamma square divided by 2mc square. E gamma is the energy of the gamma rays and m is the mass of the emitter that is emitting the gamma rays and c is the velocity of the light. So it is very obvious that m greater, er less will be lesser. So recoil takes place to conserve the momentum. Greater the mass of the emitter, lesser the recoil energy. So for solid samples the recoil energy will be less, so or equal to 0. Okay, so usually the nucleus is kept in crystalline solid and then studied so that the ER is equal to 0. So gamma ray energy for emitter will be equal to transition energy minus recoil energy. For absorber, the gamma ray energy will be equal to transition energy plus recoil energy. Okay. So this I have already discussed in the previous video. Then recoil energy, after that isomer shift. So isomer shift, which is also known as the chemical shift, it is the result of change in electron density at the nucleus, which produce small change in the nuclear energy levels. So nuclear energy levels, there is change is produced because of the change in the electron density of the nucleus. For example, emitter will be having one electron density and absorber will be having different electron density. So there is a increase in the energy of the nuclear energy levels. So that is known as the isomer shift. So that is shown here by means of the diagram. Okay, it is represented diagrammatically. The isomer shift is here. Between the emitter and absorber is represented diagrammatically. Next, let us see with an example now. Let us take Fe2 plus and then Fe3 plus. So here the electron density differs. Okay, but the element is same, ion only, but the electron density differs, so there will be an isomer shift here. So the electronic configuration for the Fe2 plus is argon 3d6 4s0. How do we get this? So what is atomic number for iron? So it is a 3D series. It is in the 3D series: scandium, titanium, vanadium, chromium, manganese, and iron. For scandium, the atomic number is 21. Then for iron, the atomic number is 26. Okay. Argon atomic number is 18. So 26 minus 18, remaining is 8. So we can write the atomic number, electronic configuration for the iron to be argon. Okay, so 3d6 4s2. Like that you can write the electronic configuration for the iron. Argon, whose atomic number is 18, and in 3d6 then 4s2. So you get 26. This is the electronic configuration for iron. For iron 2 plus 2 electrons we have to remove from the s orbital. So argon 3d6 4s0. Okay, for Fe3 plus 1 more electron we have to remove. Argon 3d5 4s0. It's an off-filled configuration, it's a stable configuration. Okay, because d orbital can hold 10 electrons. So this is off-filled configuration, which is a stable one. Okay, so it is well known here that the electron density is more for the Fe2 plus than the Fe3 plus. So the greater d electron screening is there for the Fe2 plus. So this naturally causes a shift in the nuclear energy levels. Okay, that causes the isomer shift. See, so the absorption of gamma rays by the absorber takes place only when the energy levels of the source and absorber becomes equal. So there is a shift actually, but only when they are equal only absorption will take place. Okay, so this is achieved by moving the source towards the emitter or away from the emitter. So that is known as the Doppler effect. If the energy level of the absorber is greater, okay, is greater in energy than the of the emitter, then the source must be moved towards the sample. Okay, if the energy levels of the absorber is less in energy than the emitter, then source must be moved away from the absorber. Okay, so by means of Doppler effect we can match the energy and then resonance can take place. So mossbauer spectra looks like this. It's the intensity of gamma rays versus speed of the source. Okay, so when the absorption takes place, a peak is obtained here. So intensity of the gamma rays will be 100%. So when the absorber absorbs the gamma rays, at that time there is a down in the dip in the intensity of the gamma rays. So Doppler effect, that is shift in frequency, delta mu is equal to mu v divided by c, where mu is the frequency of the source and v is the velocity of the source. So the shift in frequency can be calculated by this. Okay. Okay, quadrupole splitting. So quadrupole splitting occurs for iron 57. Ground state I is equal to 1 by 2 and excited state I is equal to 3 by 2. So first of all there will be a isomer shift, and after that the ground state, that is I equal to 1 by 2, there is no quadrupole splitting, because the splitting is governed by the rule number of split is equal to I plus 1 by 2. So 1 by 2 plus 1 by 2 is equal to 1. So no splitting for I is equal to 1 by 2. Okay, so the ground state is not split. No split for the ground state. For the higher energy state, 3 by 2 is I is equal to 3 by 2. So 3 by 2 plus 1 is equal to 4 by 2, that is equal to 2. Okay, so the higher energy level 3 by 2 splits into 2, plus or minus 3 by 2 and plus or minus 1 by 2. Okay, so difference in energy level is given by delta EQ, quadrupole splitting energy. So two transitions are possible here, plus or minus 1 by 2 to plus or minus 1 by 2 and plus or minus 1 by 2 to plus or minus 3 by 2. So two peaks are obtained in the mossbauer spectra. Okay, the selection rule for the transition is delta is equal to 0, comma, plus or minus 1. So only that transition is possible. In mossbauer spectra, I have given here mass spectra, that's a mistake, mossbauer spectra. So for absorber with the nuclear angular momentum, quantum number I greater than 1 by 2, the non-spherical charge distribution results in quadruple splitting of the energy states. For example, ion with a transition from I is equal to 1 by 2 to 3 by 2 will exhibit a doublet of individual peaks in the mass pair spectra due to quadruple splitting of the nuclear state. Okay, so next is in the presence of magnetic field. We are going to see about hyperfine splitting. So there is isomer shift and then the quadruple split, and in the presence of the magnetic field, hyperfine splitting will occur. Okay, so that follows delta m is equal to 0, 1. The transition, such a transition only allowed. So in the presence of magnetic field, the interaction between the nuclear spin moment with the magnetic moment is removed. Removes all the degeneracy of the energy level, resulting in the splitting of energy levels with the nuclear spin I into 2I plus 1. So in the presence of magnetic field, degeneracy is removed. That is, the energy levels are no more equal in energy. They are splitting. So that splitting followed by 2I plus 1. So number of splitting is equal to 2I plus 1. So if I is equal to 1 by 2, substitute there, then you get 2. So the level plus or minus 1 is split into 2. And the level 3 by 2 is split into 4. So if you substitute I is equal to 3 by 2 in 2I plus 1, you get 4. So 3 by 2 is split into 4, and I is equal to 1 by 2, energy level is split into 2. Transition, it follows I delta m is equal to 0, 1. So although 8 transitions are possible, in that 2 transitions are forbidden. That is minus 1 by 2 to minus 3 by 2, plus 1 by 2 to minus 3 by 2. So these 2 transitions are not occurring. So although 8 transitions are possible, only 6 peaks you will be getting in the ratio 3 is to 2 is to 1 is to 2 is to 3 for the mass pair spectra. Okay, because the transition, the selection rule for the transition is I delta m is equal to 0, 1. So although there are 8, okay, only 6 peaks will be obtained according to the selection rule. Chemical shift, there is isomer shift. Definition is already discussed, but depends upon 3 factors: electronegativity of ligands, oxidation state, and then pi acceptor character. So electronegativity for fluorine is greater. So greater the electronegativity, so greater the isomer shift is also. And oxidation state is lesser, greater the oxidation state of metal is lesser, the greater the chemical shift or isomer shift. And then pi acceptor, the triphenyl phosphine is a greater pi acceptor. It is having greater pi acceptor character. So but its isomer shift will be less than the trimethyl phosphine when it is acting as a ligand. So isomer shift depends upon electronegativity, oxidation state, and pi acceptor character of the ligand. So for this 3 examples given here, and isomer shift is equal to K Re square minus Rg square and psi s square minus psi s square for the absorber. Okay, so first factor is for the source. So Re is radius actually of the excited state, and Rg is the radius of the ground state, and psi s naught is the electron density for source, psi s a is the electron density for absorber. Okay, so first isomer shift is asked, first definition should be written, and then factors, and then the formula can be given. So increase in electron density decreases isomer shift, increase in d electron density, more shielding will be more for the s electron density, so isomer shift is increased. This spectroscopy gives structure and bonding informations and finds application in bio, inorganic, biomedical and steel industries.